Hello students, welcome to lecture 22. Um, just to recall you that we are discussing phase control rectifier, where we in the previous class we discussed about half wave phase control rectifier, right? So unlike diode rectifiers, we observed that we understood in the previous session phase control rectifiers has advantage of controlling the output voltage, right? So the diode rectifiers are called uncontrolled rectifiers because you cannot control the output. Once the diode is conducting, you will be getting the output across, say, positive cycle or both the cycle, depending on whether it is half wave rectifier or full wave rectifier. While if you replace these diodes with thyristors, you have understood in the previous class that it becomes a phase control rectifier, right? Where the output voltage can be controlled by varying the firing angle, right? Firing angle of the thyristors. So the time at which you turn on the thyristors, you will be controlling the output voltage across the load. Okay, so these phase controlled rectifiers find their application in mainly in speed control of the DC motors, or the applications wherever you come across motors with speed control. Okay, so as I said, just to recall you, in the previous session, we discussed half wave control rectifier with resistive low. So you have different categories there. You can understand this single phase half wave controlled rectifier with the R load as shown in the figure here, or you can also understand this circuit, that is single phase half wave rectifier, control rectifier with RL load, also with RL load with freewheeling diode. Okay, so these are the different categories what I'm just naming now. Along with this, you also have single phase full wave control rectifier. Okay, here in the circuit, what you can see here is a half wave controlled rectifier. You observe there is only one thyristor. So full wave means you can use two thyristors, wherein you can call it as a center tapped type of full wave rectifier, or if you are using bridge rectifier circuit, you will have a you will call it as single phase full wave bridge converter. All right, so there again you can understand the circuit with R load or RL load and RL with freewheeling diode. Okay, so according to your syllabus, now you have a single phase full wave control rectifier with RL load only. All right, so by the end of this session, you will be able to describe single phase full controller with RL load. Okay, observe the different terminologies what I'm using here. Till now I was saying full wave control rectifier. Okay, you can also use the term full converter. All right, full wave control rectifier or full converter. So single phase full wave control rectifier is same as what you are having here, single phase full converter. All right, so before going to RL load according to the syllabus, first I will explain with R load so that it will help you to understand with RL load. All right, so this circuit what you can see here, it is a single phase full wave control rectifier. See, I have used both the terminologies there so that you will get familiar and understand that both mean same. Full wave control rectifier is same as full converter. All right, so the circuit shown here is single phase full wave control rectifier with R load. So as you can see, it's a bridge circuit wherein you might be aware that the full wave rectification or the output, what you can imagine there, it will be because of the two devices conducting at a time, right? In first half cycle, two devices, that is T1 and T2, will be conducting, and in the next half cycle, T3 and T4 will be conducting. Okay, so again, similar to the full wave rectifier circuit, where now you have diode replaced with the thyristors. That's why the name T1, T2, T3 and T4, all these are thyristors. All right, and your load is single R type. So understand the working here. So um, you know that in the positive first half cycle, okay, in the positive first half cycle, the the thyristors T1 and T2 will be conducting. Okay, so the flow will be, the current flow will be via, say I have named here the points L, T1, A, the R load, B, T2 and N, right? So this will be the path of the conduction or the current flow, right? So remember here, now when you are using thyristors, obviously there will be a thyristor triggering circuit at the gate terminals, which is not shown here. Okay, but you should always understand, whenever thyristors are used at gate terminal, there will be gate triggering circuit. Okay, you need triggering circuit to turn on these thyristors, all right, which is not shown here. Remember that. All right, now to turn on T1 and T2 in the first half cycle, obviously I need a triggering circuit, a same triggering circuit, which would be triggering both T1 and T2 at at a single time, or parallelly or simultaneously, right? So I need a same triggering circuit, where the triggering circuit will be triggering T1 and T2 at the same time. All right. So observe here, the first waveform what we have here is indicating Ig1 and Ig2. That is the gate current that you are giving to terminal G1 of thyristor T1 and G2 of thyristor T2. Okay, so imagine that you have used the same triggering circuit, and this is the pulse what you're giving here. So this is nothing but your Ig, that is the gate current, okay, which will be same for G1 and G2. All right, so in the positive first cycle between 0 to pi, in the positive cycle, imagine at alpha you have given the gate current Ig1 and Ig2, which will be turning on T1 and T2. Okay, when T1 and T2 are turned on, then the circuit will be complete, and the voltage what you apply here, Vs, will be appearing at the load R, right? Okay, now let us observe the output. If you are measuring the output across R, the load, okay, this is your output V0. Okay, observe there. So till the thyristors were not turned on, there is no output across R. Okay, the moment you have turned on T1 and T2, the input what you have applied is appearing at R. Okay, so from the instance that is alpha, say if your triggering signal is coming at alpha, from alpha to pi, you are getting the output. The input appears at output, that is across R, right? Okay, so once the input signal is going negative, you know that T1 and T2 will be turned off, right? So during the negative cycle, this will be negative and this will be positive. Okay, this point will be positive. So T1 and T2 will obviously get turned off. Now observe, there is no output here, isn't it? Why is that so? Because the next devices are not turned on. That is, according to our explanation, T3 and T4 should turn on, so that you will get output in the next half cycle, right? But you are using thyristors and you need to turn it on. So observe here, this is your indication of the gate current which you have given at T3 and T4, indicated as IG3 and IG4. So you are using the same triggering circuit to turn on T3 and T4. All right. Okay. So imagine this is your pulse, what you're applying at pi plus alpha, at instance pi plus alpha. Okay. So the moment you are giving this gate signal IG3 and IG4, T3 and T4 will be turned on. All right. So in the negative half cycle, the conduction, that is the input, will be appearing at R. All right. So look at the output voltage here. You are getting output voltage at this point, that is from instance pi plus alpha to 2 pi. Correct? So then again, you see, as there is a reverse voltage, input voltage, it is getting turned off. All right. So this cycle repeats. So observe the voltage there, output voltage. Initially up to alpha there is no output. From pi to pi plus alpha there is no output. All right. Similarly, current as well. Current is also appearing uh, at the same point like when you have the output voltage. So this is your output current as indicated in the waveforms. Okay. This waveform, it is the voltage across thyristor T1 and T2. Okay. So T1 and T2 voltage will be same. Till it is turned on, the same input voltage will be appearing across T1 and T2. The moment a triggering signal is given, the T1 and T2 is turned on. So when the device is turned on, you know that voltage across it will be 0. So that's what is indicated here. And when the input voltage is going negative, T1 and T2 will be turned off. So when it is turned off, the same input voltage is appearing across T1 and T2 till it is turned on next in the next cycle, right? So similarly, look at this second half of the period there, wherein you are giving triggering signal to T3 and T4. Okay, so till you are giving triggering signal to T3 and T4, the input voltage, you can imagine the reverse phase there. It is appearing across T3 and T4. The moment you are applying triggering signal at pi plus alpha, T3 and T4 is turned on. So voltage across them, that is T3 and T4 both, it will be 0. Okay, similarly in the next cycle, it will, the same input, that is in the reverse phase, it will be appearing across T3 and T4. So please go through this waveform and try to understand. Okay, so this will be voltage and this will be the current. And if you observe, the current is having ripples, right? So there is current and there is absence of the current in the circuit for a duration, and again it is appearing. So it means there is ripples there. Okay, similar to the output voltage. So to overcome the ripples or to have continuous current at the output, all right, we can use inductor there. Okay, so let us see the explanation with RL load when you insert a inductor there. All right. So, sorry. Yeah. So in these slides, I have explained the same thing. What I have explained is put up here. You can go through, pause, and you can go through. The same explanation is given here. So one thing to understand here is the output voltage here you can control obviously by controlling the alpha. Yeah, the the time at which you decide to turn on the devices, that is thyristors, you can control this output voltage, right? So that's why the name controlled rectifier or converter, because you can um, control the output voltage that is appearing across load, right, by controlling the alpha or the firing angle. So that I have shown here and explained here. Please go through. You can pause and go through the slides. All right. Um, Let me go to actual syllabus, that is single phase full wave converter with RL load, or also called fully controlled rectifier. All right. So as you can see again here, you have RL load, there is inductor and resistor, and you have used four thyristors in the bridge network, so which is nothing but your full wave converter. So you can go through these slides which I'll be explaining now. Okay, the explanation is already given in the slide here. So similar to the explanation what I had done for R load, okay, now in RL load what happens? Okay, so in the positive cycle, similarly T1 and T2 will be conducting, and in the next half cycle T3 and T4 will be conducting depending on the triggering signal. So triggering signal will be given by the triggering circuit for T1 and T2, okay, at instant alpha, and at instant pi plus alpha T3 and T4 will be turned on. Okay. Now observe here, when at alpha, if you are giving a triggering signal, when T1 and T2 are conducting, we know that the current flow will be from L, T1, A, L, R, B, T2 and N. Okay, don't get confused with this L and inductor L here. This is just a name L. Okay. Let me say, repeat it. L, T1, A, I will call this as a whole load. Then point B, T2 and N. Okay, this will be the current flow. So observe here what happens in the positive first half cycle, that is 0 to pi, in this duration. T1 and T2, it is conducting, it is forward bias and it is conducting, there is a current flow or the circuit is complete, and the input what you are applying is appearing at the load. So that is what you can see here. Okay, once T1 and T2 are conducting, the input what you have applied is appearing at the load. All right. Now, because of this inductor, you know the property of the inductor. Okay, even when the input signal is going negative, the inductor current is still there in the circuit, which keeps the T1 and T2 on even during the negative cycle. That is for small duration of time. Okay, so depending on the value of L, so this current will be there in the circuit, which will keep T1 and T2 on even during the negative the of the input signal. Okay, when the input signal is in the negative or the reverse direction, because of the inductor current in the circuit, T1 and T2 will be still conducting. So that is what is shown here. Okay, so during this period, if you observe, okay, so during the period alpha to pi, you have output voltage positive, okay, and current is also positive. Okay, so during the duration pi to pi plus alpha, the output voltage is negative, all right, and the current is positive. Okay, there is still current flowing in the circuit as because of the presence of the inductor. Okay, next in the next cycle, observe that you are triggering uh, T3 and T4. Okay, the moment the input voltage is going in the next cycle, that is between pi to 2 pi, So when you are triggering T3 and T4, T3 and T4 will be conducting. Okay. So the input voltage is appearing at the output. And again, because of the inductor, when the uh, input voltage is going in the reverse direction, still T3 and T4 will be will continue to conduct. Okay, so you can see the output voltage going in the reverse direction. If you observe the current will be varying like this. So when the output voltage is going negative, current will be dropping, but because of T3 and T4 conducting again, current will be raising. So if you compare the current to the previous discussion what we had with R load, here in this duration current was 0, but here you do have current in the positive potential, right? That is there is current, positive current in the circuit, all right, but there is still a ripple, right? So there is variation in the current, but this variation or the ripple in the current, as I said, it can be controlled by the value of L. Okay, which means higher the value of L, that is higher the inductance, the ripple in the current will be lesser, which means that you can have continuous current by increasing the value of the inductor. Okay, the current can be made continuous by increasing the value of the inductor. So the other two waveforms here, it is similar to what I explained just now. These are the voltage across thyristor T1 and T2. Okay, between 0 to pi, you can see initially the same input voltage will be appearing at T1 and T2, and when it is turned on, it will be 0 till the next cycle. Okay, and T3 and T4 similarly, the input voltage in the reverse phase will be appearing at T3 and T4 till it is turned on. When it is turned on, the voltage across T3 and T4 will be 0. Okay. So the average output voltage, as we discussed just now, the output voltage can be controlled by varying the alpha, right, between 0 to pi, by controlling the phase angle, that is firing pulses, that would be applied at the gate terminals. Okay, the output voltage can be controlled. So the average output, that is DC output voltage, can be obtained by the expression um, EDC is equal to 1 by pi between alpha to pi plus alpha. Recall the waveform there. So input, if you are taking it as Em sine omega t d omega t, then substituting the limits, you get, taking Em outside, you can take it as Em or Vm. Anything, any expression is fine there. It is the magnitude of your input voltage. Okay, by applying the limits, the output voltage can be given by EDC, average output voltage EDC. It is given by 2 Em by pi cos alpha. Okay, so if you take it as Vm, then it will be 2 Vm by pi cos alpha. So this is the average output voltage for the full wave converter. All right, now if you observe from this, the output voltage EDC, okay, can be varied between 2 Em by pi to minus 2 Em by pi. Okay, which means that, I mean to say, by controlling alpha, the output voltage can be varied between positive to negative. That's the meaning. Okay, positive 2 Em by pi to minus 2 Em by pi, isn't it? So that's what, by controlling alpha, you can control the DC voltage between positive and negative values. That's why we say we get the output in two quadrants in this type of converter. Okay, so one more point to observe here. During the interval alpha to pi, I'll go back to the circuit. 1 minute. Uh, during the output alpha to pi, observe there the supply voltage is positive and the current is also positive. Okay, so which means that the flow of power is from AC source to load. Okay, observe here the output voltage is positive and current is also positive, so which means the power flow of power will be from AC load, sorry, AC source to load, that is supply to load. All right. So in this case, if alpha value is less than 90, then we say that the power flow will be from AC side to DC side. So this converter, it will be, we say that it is operating as operating in rectifying mode. Okay, when alpha is less than 90 degrees. All right. So if you observe alpha is greater than 90 degree, what happens? Observe here the output if alpha is greater than 90 degree. Say you are triggering here after 90 degree. What happens? How will be the output? Your output voltage will be, say, starting from somewhere here, and this negative part would be extending here, right? I hope you are able to follow my pointer there. If you are triggering your T1 and T2, say after 90 degrees, okay, say somewhere here. So output voltage will be appearing from this point, isn't it? Instead of here, it may appear somewhere here. But in this negative cycle would be also extending this side, which means the output voltage will be more negative, correct? Okay, so but the current will remain positive. So then we say this converter is operating in inverting mode. Please understand that. Please understand, if the alpha is greater than 90 degrees, then the output voltage will be negative, okay, and current is positive. Then we say that the power flow is from load to supply. We say the power flow is from load to supply. So which means the converter is operating as a inverter, or it is operating in inverter mode. Okay, all these are important points that has to be followed and understood. Okay, uh, okay, that's all. Please go through the session. If you have any doubts, you can get back to me. Yeah.